Sebastian Steger is a software engineer at Akisoft Pegasus. He is a graduate of Technical University of Berlin, Germany, where he studied computer engineering, focusing his research in digital imaging and lossy image data compression. In this presentation, Sebastian is going to talk about the fundamentals of lossy image data compression. Rather than just describing how images are compressed in well-known formats like JPEG, the focus is more on conveying the underlying principles in an intuitive way. After a general overview of lossless and lossy data compression, each component of a typical image compression technique like JPEG or JPEG 2000 will be described.
In the last 20 years, storage space for computers got bigger and bigger and cheaper. So why even deal with compression? Storage of data is not the only thing to consider. Smaller files also result in faster transmission over a channel with limited bandwidth, like the internet. Let me give you two examples that show how essential the compression of image data is. For digital cinema, each up to 4000 times 4000 pixel frame is compressed individually. Despite the fact that compression is applied, the bitrate gets up to 250 megabits per second. A 90-minute movie occupies roughly 170 gigabytes of disk space. Another example is computer tomography in the medical world. Depending on the examination and the CT device, a single examination requires roughly 700 megabytes of disk space. In some countries, it is required by law that all examinations are stored for at least 10 years. You can imagine that this results in an enormous amount of data. Let's first talk about lossless data compression, meaning that the decoded data is binary identical to the original data. For lossless compression, the only thing we can really do is to describe information more efficient compared to its natural description. That means we have to get rid of as much redundancies as possible. Redundant data is data that a receiver can already derive from the data that he had received before. That means that the data does not result in an information gain for the receiver because he knew all information in advance. Let me give you an example for achieving compression by simply describing data more efficiently. For the given sequence, the natural description is to store each item individually. Because of the many similarities amongst adjacent items, the following description saves a lot of data. Here I always encode how many of the same item occurs, followed by the value of the item. This clearly is a more efficient representation for that specific sequence. The approach is called run-length coding. Like any compression method, this only works if the data fits our model, meaning here that the data is highly repetitive. The following sequence shows that if the data does not fit to our assumptions, compression cannot be achieved, and even worse, it results in data expansion. Lossless compression is applied whenever it is required that the decoded data is exactly the same as the original data. Binary data like executables and text are good examples. For images, it is typically sufficient that the decoded image looks close to the original image. But sometimes even for that, lossiness is required. Some countries require by law that medical data must be stored without any loss, and for example, NASA's Spirit rover transmitted image data using lossless compression. The table here illustrates what compression typically can be achieved for various lossless compression methods for three different types of images. A very simple image that is very repetitive, a natural image, this one is called Lana and is very commonly used within the image processing community, and an artificially created image where each pixel was independently assigned a random value. Since BMP files store the value for each pixel independently without using any compression, we use it as our reference. For the simple image, all applied methods perform pretty well. For the natural image, you can clearly see that compression methods that are tuned to that kind of image data, like lossless JPEG 2000, and JPEG LS, perform significantly better than, for example, just storing the image in a zip file. For the artificial image, no compression method seems to be suitable. In fact, the natural description performs best. The reason for that is that no assumptions whatsoever can be made about the image. If we allow that the decoded data is not identical but some sort of loss is tolerated, we can do more than just describing information in a more efficient way. We can simply omit information that the receiver does not really need. For images, that is information which the receiver is not able to perceive at all, like a fine graduation of each individual pixel, or is tolerated, like a slightly blurred version of the image. Basically, two techniques are common to remove irrelevant information in image data compression. The first is subsampling or downsampling, which just reduces the resolution of the image. A simple way to do that is to assign the average of, let's say, 4 pixels in the original image to one single pixel in the downsampled image. The second common technique is to describe each individual pixel with less accuracy. For example, if the intensity values in the original image range between 0 and 255, you might just map that to, let's say, 10 different values. Of course, combinations of the two techniques can be applied. Typically, lossy compression is applied to data that originated from analog signals, like images, audio, or video. Let us now define some of the basic properties of lossy image data compression. The first one is the amount of data that is used to describe information. It can be expressed by the rate, which is the file size in bits in relation to the number of pixels. For example, each pixel in an uncompressed color image is described by 3 values, the red, green, and blue intensity. Each of the intensities typically ranges from 0 to 255, which requires 8 bits. Thus, the overall rate for that image is 24 bits per pixel. Another way to describe the amount of compression is to give a ratio between the file size of the compressed image and the file size of the original image. Unlike in lossless compression, the rate that can be achieved does not only depend on the image itself, but also on the amount of loss you tolerate. Typical values of the rate and the compression ratio for natural images, like the previously presented Lena images, are a rate of 12 bits per pixel, or a compression ratio of 50% for lossless compression, as we have already seen earlier. For most images, around 5 bits per pixel, which is roughly a compression ratio of 20%, it's really hard to tell the difference to the original image. On the web, higher compression is required to increase the display speed. Images with a rate around 1 bits per pixel are not uncommon, and images still look pretty close to the originals. However, you can clearly see that there are differences. The second main characteristic is the distortion. The distortion is the amount of error that is introduced due to compression. In compressed images, it appears in the form of so-called compression artifacts. Typical artifacts that result from compression with JPEG are the occurrence of blocks in the entire image and noise around high contrast regions like text. For JPEG 2000, blurry regions are likely. Measuring the distortion, however, is not as straightforward as measuring the rate. After all, it highly depends on the visual perception of the person who views the image, and thus can differ from person to person. Research brought up many proposals for the distortion metrics, but none of them has proven to be superior and yet easy to implement. Thus, in most cases, one of the most simple metrics is used: mean squared error. Basically, you just subtract the pixel intensity values of the images you want to compare. For our case, that is the original image, here denoted by x, and the reconstructed image, here denoted by x hat. That difference is then squared, summed up for all pixels, and divided by the total number of pixels. Sometimes it is more convenient to express some sort of quality instead of the amount of error. That is usually done by the peak signal to noise ratio, which sets the maximum intensity in an image in relation to the mean square error on a logarithmic scale. The plots here show the relation between the rate and the distortion or quality respectively for a typical natural image. Of course, the more data you use to describe it, the better the image looks. 3 different compression methods are compared here to each other. the well-known JPEG, its successor JPEG 2000, and the relatively new method HD photo, which was recently introduced by Microsoft. From those three, on that image, JPEG 2000 seems to outperform the others. However, since the used distortion metric mean squared error does not reflect the visual perception very well, the perceived quality ranking might be different.